Now I am going to present a toolkit we have developed which allows reusing the resources from the Apertium rule-based machine translation system into the Moses phrase-based statistical machine translation system, so we are going to get richer translation models. I will start with a short introduction, then I will briefly describe how Apertium translates, although it has already been described by other speakers. Then I will highlight some related approaches. After that, I will explain how our toolkit implements this hybrid approach, how fresh pairs are generated from Apertium and then integrated into the Moses statistical phrase-based machine translation models. Then I will give some hints about how to use this toolkit and present some concluding remarks. To start with the introduction, well, as I just said, here we are combining statistical machine translation. These systems are easy to build when we have a parallel corpus, big enough, and rule-based machine translation. So these systems encode explicit linguistic knowledge, but before this is required to build them. But when we don't have a parallel corpus, it may be very useful. But if we have both a parallel corpus and rule-based machine translation system, why don't we combine both resources to build a richer system? That's what our toolkit, which is called rule-to-phrase, does. Basically, our toolkit takes the Apertium linguistic resources, the dictionaries and the transfer rules, and generates a set of bilingual phrase pairs with the following command. And once they are generated with a different command, toolkit runs the Moses training pipeline, but in addition to the parallel corpus, includes the bilingual phrase pairs we have just generated with different strategies that we'll explain later. And once the phrase-based models are built, the translation is carried out with the stock decoder from Moses. Then, about Apertium, well, as you probably know, it's a transfer-based, rule-based machine translation system. As all the transfer-based system, they have a source language intermediate representation and a target language intermediate representation. In this case, these intermediate representations are quite simple. They contain lemma, part of speak, and morphological inflection information, as we have seen in the previous talk. It doesn't perform a full parsing, but a shallow parsing. And it is free open source, and get more information in this website. Here we have a small example of how Apertium works. Imagine that we want to translate the Spanish sentence, gatos listos, which means smart cats. It is first analyzed to get the source language intermediate representation. So we have, for the first word, the lemma is gato, it is a noun masculine plural, and for the second word, the lemma is listo, and it is an adjective masculine plural. Then we run the transfer to get the target language intermediate representation. In this case, first, the lexical transfer, which uses bilingual dictionaries and provides a word-for-word translation. In this case, the translation of gato was in Spanish cat in English, and the translation of listo is smart. And we also have a structural transfer, which contains rules which are applied to sequences whose word-by-word translations wouldn't be correct. In this case, we will have a rule that swaps the order of an adjective and a noun. So we have smart cat. And finally, the generation step, we obtain the surface form, the final surface form, final translation, which is smart cats. Okay. After that, well, we have some other approaches in which resources from Apertium or from other rule-based machine translation systems are reused to enrich a phrase-based statistical machine translation system, such as the one by Chayers, in which bilingual dictionaries from Apertium are appended to the training corpus of a phrase-based system, or the one by Seattle, in which the source text is translated with a rule-based machine translation system. Then we have a small parallel corpus. a phrase table is learned from this parallel corpus and then appended to the original one, to the original phrase table of the phrase-based system learned from a big parallel corpus. One of the problems with this approach is that to align such a small parallel corpus, the one generated by the rule-based system, they need an external alignment model learned from a bigger corpus. And so, with not a big corpus is available, we probably obtain weight alignments here. Now I'm going to describe how our system performs the different steps, the first pair generation and the first pair integration in the Moses training pipeline, well, some implementation details. So, as I said before, the phrases, firstly, first pairs are generated from the Apertium resources. We need to generate all the first pairs that encode all the linguistic knowledge present in Apertium. On the one hand, we generate phrase pairs which encode the knowledge from the lexical transfer, which is only the expansion of the bilingual dictionary. That's in this example, we have cat or cat. And we, of course, could also have multi-word entries in the bilingual dictionary, so we could have por otra parte, which means on the other hand in English. And we also generate, we also want to encode the linguistic knowledge present in the structural transfer rules, the ones that process sequences which are not correctly translated word by word. This case is more or less the same. We generate sequences of words which match the source side of a structural transfer rule and apply the rule to this sequence. For instance, for the rule determiner plus noun plus adjective in Spanish, we have la casa verde, the green house, it's for the noun, the adjective, or una casa azul in Spanish, which means a blue house in English. But here we could have a problem. Is that if we for this rule, for instance, if we combine all the determiner plus as the noun plus as plus all the adjectives, we could end with a combinatorial explosion. And this example rule is very short, but we could have much longer rules. In addition, we would generate some phrases with no semantic sense, which are useless when trying to translate a real text, such as el niño inalámbrico, which means the wireless boy in English. So the solution to this problem, well, in the experiments we carried out previously to validate this hybrid approach, we only generated phrase pairs whose source side is present in the text corpus, which is okay to know if the approach is correct, if the Apertium data helps, but in the real world, if we want to put a system with this approach in production, we need to generate phrase pairs simply which are likely to appear in the text to be translated but we may not know this text before. So the path we followed in the rule-to-phrase toolkit is to provide it with a list of allowed engrams. So we could extract this list of allowed engrams from the text corpus, and when generating phrase pairs, when we have a candidate phrase pair generated from a rule, we extract engrams from it and check that all the engrams are in the list of allowed engrams. Only in this case, the generation process continues. And these engrams could also come, for instance, from a source language model, in which we only select the engrams with the highest probability, or from a bigger corpus from the same domain than the text we expect to translate with a hybrid system. And here we have a lot of different options to test. But up to now, our toolkit only implements the function of extracting a set of engrams from a given text. Now let's see with an example how the process of generating phrase pairs from transfer rules is carried out. So imagine that we have a rule file with a preposition, plus a determiner, plus a noun, plus an adjective, one possible list of lexical forms in source language, in this case in Spanish, is this one, is el gato inalámbrico. And if we are working with trigrams, so we extract the first trigram from this candidate phrase and check that it exists in the list of allowed anagrams, and if it exists, okay. But we check this other trigram and we have that it doesn't exist. So we throw away this candidate phrase pair and proceed to another one. Note that here that we are generating the phrases matching transfer rules are in the source language intermediate representation, because the rules match this intermediate representation in items, but not surface forms. We later will generate the surface forms. And we also could generate from that rule this sequence of lexical forms, el gato, but instead of inalámbrico, listo. In this case, the first trigram is found in the list of allowed n-grams, and the second one is found too. So we are going to generate a phrase pair from this sequence of words in the source language intermediate representation. So we run the stock Apertium transfer, and we get the source language, the target language intermediate representation to the smart cat. And then we run the stock Apertium generator, and we obtain the target language the target language surface form. And as we also need the source language surface form, here we take the Apertium analyzer and we have built a module that takes the dictionary for analyzing and reverse it, and we obtain from the source language intermediate representation the source language surface form, and we end with this final phrase pair. Note that we have also obtained alignments between the different words of the phrase pair. We have obtained it in each step, and in the end we combine them. So we have that first 1, that I is aligned with 2, 2, that loss is aligned with the, 3, 4, that gato is aligned with cat, and listo is aligned with smart. And we repeat these steps for all the possible sequences which match the allowed n-grams to get a list of phrase pairs. Now once we have obtained this list of bilingual phrase pairs, we integrate them in the Moses training pipeline. Our toolkit supports 3 different methods. We could add these phrase pairs to the training corpus directly. We could add them to the phrase table, and we could add them to both. Now I'm going to give more details about each of these 3 methods. Here we have a figure representing the Moses training pipeline. So we have a parallel corpus. It is first aligned. So we have word aligned sentences. From these word aligned sentences, we learn a distortion model. We also learn a probabilistic dictionary, and of course we learn the main component, which is the phrase table. To do so, we extract phrases compatible with the word alignment, so we have a list of corpus extracted phrase pairs, and then our score by relative frequency, and also using the probabilistic dictionary from lexical weightings to get the phrase table. If we add the Apertium generated phrase pairs to the training corpus, this new data is reflected in the distortion model, in the probabilistic dictionary, and in the phrase table, of course. This approach has one potential problem, which is that in the phrase extraction step, as Apertium phrase pairs are in fact considered as full sentences, they could be split in smaller units. And one advantage over the approach by Isel et al. Is that we do not need a big corpus to be able to align the rule-based machine translation sentences, because here we have included the full bilingual dictionary. Here we have included many bilingual phrase pairs obtained from the rules, and we have enough data to learn a relatively good alignment model. Here we can see an example of the parallel corpus on the phrase table when using this approach. So imagine that we have in the original parallel corpus this sentence pair, in black, and we add these ones generated from the Apertium data. So when fresh pairs are extracted from the parallel corpus, we have more fresh pairs because these sentences have been split. For instance, we could have that this adverb is por otra parte in Spanish and on the other hand in English. We have a version of it which lacks the word hand because of the phrase extraction algorithm. And so in the phrase table, we, for instance, could have these two entries and probably with the same probability. Another option is to add the Apertium phrase pairs directly to the phrase table in the scoring step without adding them to the parallel corpus. In this case, we use the alignments obtained before because we don't align the Apertium phrases. And in this case, they are not split in smaller units. Let's see with an example. We have in the parallel corpus only the original sentence. In the list of extracted phrase pairs, we add directly here the phrase pairs generated from Apertium, but they are not split. And so in the phrase table, they are scored by a relative frequency, as it is usually done. And we also add a binary feature function which states if a phrase pair comes from the original parallel corpus or from Apertium. And we could also add the phrase pairs in both steps at the same time, so that we have improved distortion model too. And we have the Apertium phrases included here could be split in smaller units, but the ones included here are not split. So the non-split versions have higher frequency. As before, we have in the parallel corpus the original sentences and the ones from Apertium. We have on the list of extracted phrase pairs the phrase pairs extracted from the original sentences, the phrase pairs extracted from the Apertium data, but the ones which haven't been split have a higher frequency because one of them comes from here and the other one has been inserted here directly. So for instance, for the example of this upper program party on the other hand, we have that the non-split version, the full version, will have higher probabilities. And well, some implementation details. We have that the source code of this toolkit is licensed under GNU GPL license. All the actions are encoded in a file. We have a Python command line interface to provide the different options. And the modules are written in different programming languages. To obtain the alignments between words, when we generate the phrase pairs from Apertium, we had modified the Apertium engine in order to output this information. And well, when using the toolkit, well, it has been downloaded from this URL. We have evaluated this hybrid approach in different scenarios, and we have that it is very useful when the training corpus, the original training corpus is very small. This logic, we have only a little bit of linguistic information, and we add all the information from Apertium. The resulting system will outperform the base one. The system has been also useful when we have a parallel training corpus from a specific domain, and the resulting system has to translate text from the general domain, as the information included with Apertium is from the general domain too. We saw it in the WMT workshop of the last year, as our system wasn't outperformed by any other system. In this workshop, participants were given a parallel corpus from the politics domain, this was Europar, and asked to translate some news-related texts. And when building a hybrid system combining the Europal text and the Apertium data, we get a very good result. It is also very useful when translating highly inflected languages. Some of the forms of the words may not be found in the parallel corpus, or they may be sparsely found. And finally, we haven't found significant differences between the three strategies used to integrate the first pairs into the Moses models. And so finally, to conclude, I would like to remark that we have developed a free open source toolkit which allows to integrate Apertium resources into the Moses models. We have some scenarios in which this approach is highly effective. And in the future, we plan to study how to generate this list of allowed n-grams from a source language model, so that we can generate fresh pairs which are likely to be found in the text the final system will have to translate. And we also plan to study more deeply the differences between the integration strategies. And well, we expect that the translation community reuse this toolkit and reuse the Apertium information to build more powerful machine translation systems. That's all.
Questions?
You have used.
You're free to say something.
You have not used the cylindrical form for your data stores in your picture.
I have.
I mean, which software have you used that gave you this shape of?
This is two-dimensional.
Yeah, I mean, understand.
Yeah, I use this shape for dictionaries and then the cylindrical form for statistical data.
These are tech. So how did you make?
With BIA. BIA.
The images, I mean, the
Yes,
graph that you have.
The images are built with BIA. It's a diagram program from the Genome desktop.
BIA.
Yes, BIA.
Look, it's not cylinder.
Okay, thank you very much. Now we have.
We should have coffee now, and I think we can recon.